Hello. So in this today's class, we'll learn about force and free body diagram. In IBDP A2, this is all about dynamics. So in dynamics, we do study this motion of the object under the influence of forces. So if we see, let's say there are like two forces, F1 and F2 is acting on it, then we do calculate the net force on this object using this Newton's second law. Net force is mass times acceleration. We get the value of acceleration, and if the acceleration is zero, or if the acceleration is non-zero and then constant value, then we describe this motion using like Suvat equation. So when the acceleration is zero, I can say the object gonna be at rest or be moving with the constant velocity. Or if acceleration is non-zero but constant, then I can use Suvat equations to describe this motion of an object. In order to study the different types of forces, we have in dynamics, we have this seven kinds, which are weight, normal reaction, friction, and then tension. We'll see the list of it. So how do we study about this weight force? So in order to study these forces, we have this several kinds of forces, starting with the weight. So the weight is uh, the gravitational attraction between the two masses. So the Earth always attracts any other object towards its center. So that is the force on the object, such as the Earth. And it is calculated as mass times gravitational pull. Then we see this normal reaction force. That's also known as the support force that is exerted by the surface perpendicular to an object which has been resting on it. So in this example, when the object is lying on the floor, you see the weight forces downward, but the perpendicular force from the surface is upward. In case of an inclined plane, that support force is upward for it. Then we see this frictional force. That's a resistance force that opposes the motion of the object, which is either sliding or rolling. We understand there are like two kinds of friction. One is called a static friction and maximum static limiting value, maximum static frictional force. And there is a kinetic friction, which is like when the object is in the moving. It has been calculated as mu s into the normal reaction and mu k into the normal reaction when the object is moving. The static frictional force is always bigger than dynamic frictional force. Next kind of force is basically the tension force. So the tension force is that pulling force transmitted through the string, rope, or cable when it has been pulled tight. So it's always acting towards the fixed end, or the fixed end over here. And tension force is non-zero when the string is completely taut. You can't pull, you can't push the other object with the rope. You can only pull it. The tension will be always away from the mass. So it's always away from the mass. So as you can see in this diagram, its weight force has been pulling it down. The tension force has to pull it up. Then there is a Hooke's law as well. That's also we know the Hooke's law is the force is directly proportional to the extension within the elastic limit. So the more load you apply on this object, the spring gets more and more extended, and this the force applied and then extension is directly proportional. So that's why you get the slope as the spring constant, delta f upon delta x. The Stokes law talks about the viscous drag force. So this is the same reason why like the bottle filled with the ketchup is difficult to pour compared to the water which has been filled with. So in that Stokes law, the drag force is 6 pi eta r and then v, where this n type symbol, this is called as eta, that is basically the viscosity of the fluid, and it's measured in Pascal second. You can do the unit analysis. So Fluid with the low viscosity is easy to pour, doesn't resist such motions. Then there is a upthrust force, which is also called as force of buoyancy, or like no, the buoyant force, and that is the force exerted by the liquid um, when it is drowning or like floating. So it's the same as the Archimedes principle. You can calculate it as, and then the buoyant force is calculated as rho v g, where the rho is the density of the fluid, v being the volume of the fluid, and then g is acceleration due to gravity. So here in this, when we knew that like several forces are acting on it, then we, like on the complex object, we take one object at a time to describe what are the forces acting on it. So in order to draw the free body diagram, you always take object as the point mass. You all take this object to be a point mass. Then think about the possible forces acting on it. And then while drawing a force, you make sure that you draw the length of the arrow according to its magnitude, and then its direction according to the arrow head. And we use Newton's second law, that F net is mass times acceleration, to calculate this value. And then, as I spoke earlier, if the acceleration is zero, that is called as equilibrium, like translational equilibrium, then I can say, I can describe this motion of the object to be at rest. Or if it is like no moving, then also it has to be moving with the constant velocity so that the acceleration remains zero. If acceleration is non-zero and then constant value, then you can say it is uniformly accelerated motion. And I can use the Suvat equations to describe, like to find the velocity, displacement, and its speed after a time t, as what we did in kinematics. Just to complete this, Um, we also use Newton's laws to describe it. So the Newton's first law is about law of inertia. So the object in rest will remain in rest. Object moving with a constant velocity will remain in constant velocity until unless you apply a force on it. Then we see the Newton's second law is the net force is mass times acceleration, and third law is about every action has equal and opposite reactions. So we see the action and reaction force must be like same type of force. It must be same magnitude but opposite direction. It's on two different objects and simultaneously. So the net force on each object would be non-zero. So the example over here would be if there is a wall, and if this guy pushes the wall, then and if it is standing, let's say, on the board, then the wall is also exerting force on this guy with the same magnitude as the guy exert force on the wall. It will be same magnitude. So we may draw this free body diagram and solve it as well. So here are the few examples. You can draw the free body diagrams of it. Draw this. Let's say there's a pulley. There's this mass connected over pulley, and there's a capital mass. Let's say 10 kg. Maybe this is 5 kg. If you think about what are the possible forces acting on it, draw the free body diagram. So if you think about on 10 kg object, there will be a weight force acting its downward, which will be 100 Newton. And also this is like the string which goes over the pulley. Obviously, I've taken like the simplistic condition where the pulley is not exerting any friction between the string and then pulley. And if the same string goes over, so there will be a tension force as well. That will be slightly smaller in this case, because this 10 kg object will be accelerating downward with this acceleration. Now there will be a friction as well between this mass and then the surface. So if I give you, let's say the mu value is 0.3, then I'll be able to think about the frictional force as well on this 5 kg object. So on 5 kg object, there'll be a weight force of 50 Newton. Then there'll be normal reaction of the 50 Newton. And there will be a frictional force which will be backward. And you can calculate that magnitude using mu, which is 0.3 times its normal reaction, 50. So that's gonna be 15 Newton. And also there will be a tension force which is pulling this block to the right with the same acceleration. You can use this Newton's second law to find the value of the tension and then acceleration. So in each block, you can draw the free body diagram.